Hey,
Yeah,
I'm so glad you could join us again. Joining me on our virtual stage are Imran Desai and Peter Hoovy. They've been working as software engineers and developers in companies developing around TPMs, Trusted Platform Modules. Here, they're going to briefly tell us about remote attestation, the privacy aspects of remote attestation within TPM 2.0, and how you can customize existing attestation frameworks for your security and privacy use cases. Questions are welcome, but they're not going to happen on the stream. They're going to happen in our post talk QA chat channel, and both of them will be there after the talk. Take it away.
yeah. Hello, everyone. Thanks for attending our talk. Sorry that we run a little bit late, but that's how it is with live conferences. As said, today we will talk you to the basics of attestation and then explain you the details of the privacy aspects of it. My name is Peter Hüwe. I'm presenting from Augsburg, Germany. It's early in the morning for you, for me, and I work as a embedded software security developer at Infineon. And together with me is today Imran.
Hello and welcome to this presentation. My name is Imran Desai. I'm a security software engineer at Intel Corporation System Software Engineering Division, and I'm a developer and maintainer of the TPM2 tools project under the TPM2 software organization. Today, I will be building upon the foundational topics of device attestation that Peter is going to cover and delve into the details of the security and privacy aspects that render a TPM-based attestation trustworthy.
Yeah. In case you're wondering why are two people from different companies presenting one joint topic, this is exactly because Imran and myself and a lot of more people are working together on our little nice community effort-driven project called TPM2 software.github.io. It's a community-backed effort. That is also supported by Infineon, Intel, Fraunhofer, Red Hat, and we have a lot of hobbyists as well. And our aim in our project is to make your life with the TPM 2.0 under Linux easier. For this, we provide a TCG compliant TPM2 software stack. We also ship a lot of different tools and also provide an integration into OpenSSL and PKCS11. So and recently also there was some integration into system decrypt setup. So if you want to do some BitLocker like full disk encryption, yeah, we got you covered. Our project has this really nice community. If you want to have more details, go head over to tpm2software.github.io. And if you want to have more details about the whole software stack, how we can use it, or how we can use all that stuff, just hit up the search engine of your choice and search for my talk about using the TPM. It's not rocket science anymore. Yeah. So remote attestation. What is remote attestation? What is attestation at all? Brief disclaimer or short disclaimer. This will be a really, really quick and simplified introduction by me because there are two reasons for this. On the one hand side, Imran will guide you through the details later on, and we just want to give you a groundwork or the framework for this beforehand. And on the other hand side, most of you probably attended last year's LCA, and there Matthew Garrett gave a really nice talk about TPM-based attestation. And of course, we don't want to repeat information that already has been presented. So we will just give you a quick overview. So, uh, so what is attestation? Let's start with the beginning. To attest, it means to affirm something to be correct, true, or genuine, or to witness something. So let's start with these two persons. We have Robin, and she meets Alex and wants to trust him or doesn't know whether she can trust him. And she asks Alex, "Can I trust you?" And of course, Alex says, "Of course you can trust me. I'm a random stranger of the internet. You can trust me." Yeah, as with all random strangers of the internet, they can lie. But of course, Alex is prepared for that. He has some kind of evidence that shows that he is a trustworthy person. He wants to show his police record as evidence, but unfortunately, that police record is signed, but in a different language. So Robin cannot really read that language. that evidence is not too much of worth for her. But she has a friend who speaks that language and also happens to know Alex in person. And she asked Veronica, can you please verify this random stranger of the internet? And Veronica looks at his police record, also knows him personally, and then she can vouch for his identity and say, yes, Alex is trustworthy. Of course, these names, or the names we were just using, were not randomly made up. The initials of these names actually correspond to the roles of the IETF RATS standard. The RATS standard explains remote attestation systems. So Robin becomes the relying party, Alex becomes the attester, Veronica the verifier, and the evidence stays the same. So if we go to devices, the statement about trustworthiness always or often corresponds to whether to a statement whether the platform is in a good state. And of course, there's the dilemma. If I ask the platform, are you a good device? The platform will always respond, yes, I'm a good device. Of course, you can trust me. Because if it's good, then it will claim that it is in a good state. However, if it has been compromised, it will simply lie to you and also say it's in a good state. And to tell the difference is really, really hard. And for this, we need some help to tell the difference. And we have this little nice crypto controller or security controller called TPM, Trusted Platform Module. It's basically in every device or in every modern PC. There are also heads for Raspberries and all this stuff. So it's easy to have that in all commodity platforms. It's an open standard defined by the TCG, and it supports a powerful authorization module. It has these platform configuration registers. Please keep them in mind. A secure key storage, and true random number generators. So what about these PCRs? Why are these so important? Or rather, how can we measure that how can we record that our platform is in a good state? You can take measurements from your platform and store them within the TPM. And this specific location where you store the measurements in are the platform configuration registers called PCRs. The unique thing about PCRs is that you cannot simply write to them, but the only way you can update them is doing the so-called extend operation. The extend operation takes the previous value together with a digest, combines them, makes a hash, and stores that. This digest is actually the measurement, which is usually computed by the host machine, for example, the bootloader. So the heavy lifting is done by the CPU, and then the hash is given to the TPM, which updates it using the PCI extend mechanism. These PCRs are usually only reset at system reset, so you cannot simply reset them via software. It's also important to know that the TPM can bind secrets and policies to the value of a PCR, so you can do a lot of fancy things with that. So, next slide. Yeah. So now we want to measure our system boot. So we have this immutable boot ROM, something we cannot change or doesn't change, also called the root of trust for measurement. It computes the digest of the next stage, which is the bootloader, records the hash into the TPM, then gives control to the bootloader. This one also takes measurement of the operating system, sends it to the TPM, extends all that. Then the operating system comes, measures an application, also extends that value into the PCR. So eventually we have that log of different PCR values and the final PCR values. All these entries are also stored and maintained by the operating system in a so-called event log, which contains every entry of what has been measured. So a verifier can actually replay this event log and come to the same final PCR value, because the way how these PCR values are computed is actually known. But of course, if the operating system just reads out the PCR values, it could again lie about the PCR values. How can we make sure that it's coming from a TPM? There you use the TPM2 quote command, which generates a signature over the selected PCRs, a nonce that it has been supplied to, and then we have that signed blob about PCR values. This signed blob can then be used for verification together with the event log. Next slide. And now we come to the device attestation. The attester sends the quote and the event log to the verifier. They verify it and say to the relying party, yes, they are trustworthy. But if you have listened carefully, we are running into a privacy problem here, because the verifier now knows who I am, the relying party knows who I am, and I'm completely giving up my privacy. How can we resolve this? And this is what Imran will going to explain to you.
Thank you, Peter. Thank you, Peter, for setting up that foundational topic. The fundamental essence of a trusted attestation is that a trustworthy someone vouches that a useful something is true. And by doing that, you are inherently trusting the security and privacy mechanisms built into it to basically guarantee that information handling at every stage. So there are various stages of information handling, starting with the information generation, storage, reporting, and then processing. Together, this is called as the information lifecycle. So in that order, we're going to take a look at some of the TCG terminologies, starting with the root of trust for measurement. This is required as a collection of processes and mechanisms that guarantee the trustworthiness of the information generation process. It is expected that it is able to detect and mitigate attacks on the system and specifically on the information generation process. It is also expected that the root of trust of measurement is functionally sane. As an example, a developer wanting to shave a few milliseconds from the boot time shouldn't take the decision to simply extend fixed set of PCR values because he already verified the initial boot block and verified its integrity. It would completely defeat the purpose of the measured boot. So we expect it to be functionally sane and not do that. And it's also expected that the root of trust of measurement is immutable, which means that it behaves exactly the same from reset through runtime every single time. And that it is, from a privacy perspective, it is able to inhibit platform unique measurements going into the PCRs. Because if that happens, you can tell from an attestation code that a specific set of PCRs belong to a specific TPM, and that gives out the attester identity. The next root of trust is the root of trust for storage. This is basically providing all the mechanisms required to keep the data protected, tamper-proof at rest when it is transmitted over from the root of trust for measurement. We expect that it not only prevents data losses, but it is also able to flag unreliable data. And what that means is if you are going through an intended or an unintended power cycle and you're moving data, say, from a volatile storage to a non-volatile storage, some of that data might be corrupted. So the root of trust for storage should be able to flag such data, because critical pieces of information are used in making trust or safety decisions. It's also expected that from a root of trust of storage perspective, that there are some kind of access restrictions to who can access the data and what methods are going to be used to access that data. And from a privacy standpoint, the root of trust for storage also guarantees that there's some kind of a partitioning of personally identifiable information. And then there are some additional access restrictions to get access to those set of data. The next is the root of trust for reporting. And this is a collection, again, of processes and mechanisms that guarantee or vouch for the identity of a specific platform. Not only that we require a unique identity for the platform, we also need it to be certified by someone inherently trusted. So we prevent a self-signed certificate kind of scenario, and instead we have a device manufacturer certificate vouching that the unique identity belongs to a specific TPM. it's also expected that it enforces some kind of access restriction to sensitive operations with respect to attestation, like signing attestation codes and giving out audit digests. These are sensitive operations that need to be guarded with some kind of an authorization. And then from a privacy standpoint, we have to make sure that we don't actually use the unique identity directly into the signing operations, because unique keys create unique signatures and they can all be traced back to a specific attester platform. And thus that will compromise the attester privacy. There is also some level of trust that has to go into the attestation system software. This is the system software that is actually running on the not only just on the attester platform with the TPM, but also on the verifier or the relying party systems. At the minimum, we expect that there is a role-based access separation for data and processes of the attester, verifier, and relying party. And like Peter said, it has to protect against the replay attacks, which means that you don't use older attestation codes in fresh trust decisions. And then the attestation system software that is running at the verifier and the relying party end is able to enforce some kind of policies once it discovers that the platform is in a vulnerable state based on the attestation codes. And finally, from a privacy perspective, the attestation system software is expected to apply the principle of least privilege and prevent data leaks. So this forms the information lifecycle, and where does the TPM come into this picture? The Trusted Platform module actually directly provides the root of trust for storage and reporting in a TPM-based attestation. And it additionally provides certain features that assist the root of trust for measurement and attestation system software in the information generation and processing phases. So let's dive into some of the internals of the TPM and see how these are guaranteed by the TPM. So the inside of a TPM are very much like a hardware security module. At the heart of it is a CPU, or a place where it executes instructions that are fetched from the ROM and assisted by the RAM. And it has a clocking and reset unit. And additionally, it has, very importantly, a hardware crypto engine. And then some mitigations against brute forcing authorization. So it has a dictionary lockout protection. And then a persistent storage where data is trusted to be saved, tamper-proof. And we need, all of this is exercised through commands that funnel into the TPM through the command response buffer. And that is, those instructions are coming from the attester platform. Sometimes the attester platform executes instructions on behalf of the verifier and the relying party. And at those instances, it's simply acting as an agent. So we concluded that the TPM is a root of trust for reporting and storage. And what that means on this picture is trusted keys within the TPM are signing protected data. So let's take a look at some of the requirements of the root of trust for reporting and match them here on this slide. We said that the root of trust for reporting should be able to provide a per part unique identity. And to do that, all TPM objects actually start from a logical structure called as hierarchy, at the heart of which is a primary seed that stays persistent on the non-volatile persistent storage. And there are 4 such primary seeds. And to access the objects under these primary seeds, there are separate authorizations. So there is a separate administrator for each of these logical hierarchies. There is also a null primary seed, which lives and dies in the RAM. So TPM resets will actually change this primary seed, and it is ephemeral in nature. So all the objects that are created under the null primary seed are lost on reset. And we'll see why that is important and useful. So the first object that you create under a primary seed is a primary key using a KDF operation that combines the sensitive information from the primary seed and a attester specified key template. So basically, the key template is having some attributes and authorization policies that dictate how a key can be used and authorized. So by combining the primary seed and the non-sensitive key portion from the attester system software, we are basically going to get a primary key. As long as the primary seed and the key template remains the same, the primary key is fixed. And this actually helps us to provide the unique identity every time, regardless of the TPM going through resets. The next object that is created in line is the child object. And it is a bit different from the primary key. It additionally combines a pseudo-random value from the random number generator. This makes these keys ephemeral, which means that you could create this key, but you cannot recreate these keys because of the pseudo-random element, but you can always reload these keys on the TPM. And this ephemeral nature of keys is important for the anonymity. And we'll see that shortly. The next requirement from the root of trust for reporting perspective is that the unique key is additionally certified by the manufacturer. For the manufacturer to be able to vouch that a unique key on a remote TPM belongs to a TPM that he actually manufactured, he needs to trust two pieces of information. One, the key template that is going into the KDF operation. And he has a reason to trust that because the Trusted Computing Group Consortium defines it in the TPM standards as to what these attributes and what this key should look like. So it's a trusted piece or trusted source of information to define a unique key. And the other thing that the manufacturer needs to trust is the primary seed. For this, the manufacturer directly programs the primary seed into the TPM through the trusted factory processes. By combining these two, the template and the primary seed, and running it through the primary KDF operation, you get an endorsement primary key, which is fixed in nature. And the basic ingredients for it, the primary seed and the attributes, are coming from trusted sources. So the manufacturer is in a position to vouch for the authenticity of this key. And so he does that by assigning a endorsement key certificate. And generally, this key certificate is embedded on the non-volatile storage in general purpose NV area. One thing to note is that the TCG specified attributes prevent this key to be a signing key. Instead, it is only a decrypt key. And it is done for the reason that the unique key shouldn't be in a position to sign attestation codes because it would create unique signatures that can all be tracked back again to the attester platform. And this satisfies another requirement of root of trust for reporting, that the unique keys cannot actually sign the attestation codes directly. And so we need to provide some kind of an anonymous key to sign these attestation codes. But the requirement is that this anonymous key needs to be on the same TPM as the unique key, and it should be somehow cryptographically related to the unique key. And of course, this key has an additional attribute, which means that this key is able to sign and encrypt the attestation codes. So the root of trust of requirement for having an anonymous key that is related to the unique key is satisfied on the TPM, and we'll see how it does that. So let's first take an inventory of all the TPM. First, it has the unique identity that is vouched in for by the TPM manufacturer by issuing the endorsement certificate. Together, it is providing the certified unique identity for the TPM. And then the TPM creates an anonymous identity because the unique identity is not capable of signing attestation codes. And so the anonymous identity key is having the sign attribute set and it's capable of signing the attestation codes. And then we have the attestation code itself, which is basically a collection of data that describe the system software state. And with all of this information, the TPM is able to generate and sign attestation codes. But what it cannot do is confirm a healthy system software state. And that's where the relying party or the service provider steps in. The service provider is then handed the attestation code and the anonymous identity key, public portion, so that he's able to kind of verify the attestation code using the public key of the anonymous identity. What the relying party is not given is the unique key, which is the certified unique key. Now, the relying party can, why is that? So, this is where the basic privacy problems comes in. And the fundamental premise of that privacy problem is this. You cannot, the TPM attester or the attester TPM cannot actually give out the anonymous identity and unique identity to any entity other than the attester system software. Because combining these two will compromise the attester's identity. Think of this like an opening of a very bad suspense movie, where you have the character that is supposed to be shrouded till the end shows up on the opening scene and reveals the masked and unmasked identity. So with this setup, the relying party is able to confirm that the code is describing a healthy software state, but the relying party cannot tell that it is coming from a trusted TPM. And for this, there is another entity called a verifier. The verifier is entrusted with a interesting job. He is supposed to tell that the code is actually signed by a trusted TPM, but the verifier cannot know the anonymous identity. Why? Because the verifier will have access to the unique identity, and so it cannot additionally also have access to the anonymous identity, because then the verifier will be able to combine those two and then compromise the attested TPM's privacy. So the verifier in many ways is in a situation like a privacy CA. But unlike a traditional privacy CA, the verifier does not have access to the public key portion that he is trying to certify. So instead, the verifier takes advantage of a process called as credential activation on the TPM. It works on the, it occurs between the verifier and the attested TPM. And instead of handing the anonymous identity public portion, the attested TPM instead runs the anonymous identity public portion through a one-way function, a hash, and creates a anonymous key name. And then because it's a one-way function, anonymous key names cannot be used to reconstruct the anonymous identity public portion. So attested TPM is able to then propagate this to both the verifier and the relying party. And now the verifier uses this name, anonymous name, to run a process called as credential activation. The credential activation process is a success if the verifier is able to prove that the named object is on the same TPM as the unique key. So there are two stages of the credential activation. On the first stage, it occurs between the verifier and the attester platform, wherein the attester system software generates the anonymous and the unique keys, and then the attester platform hands the name of the anonymous key, not the public portion, just the name of the anonymous key, and the public portion of the unique key. And the verifier chooses to do a credential challenge, wherein it chooses a plain text secret and then combines the name and the public portion that was sent by the attester and runs it through a cryptographic process to wrap and encrypt the plain text secret and create a credential block, and then hands it over to the attester platform. In the second stage, the attester platform loads the sensitive portions of the unique and the anonymous keys, and then loads the and satisfies the policy authorization of the endorsement hierarchy, and then performs something called as credential activation, where he unwraps and decrypts a credential block. Now, this he's able to do only if the anonymous key and the trusted key sensitive portions are on that specific TPM. And then he's able to decrypt that credential challenge and report it back to the verifier. And the verifier then compares these two pieces of information and makes the determination that it is in fact existing on the same TPM. So he's able to certify that the named object is on the same TPM as the endorsement key. It is a myth that credential activation only works on the endorsement hierarchy. The truth is it can work with any storage hierarchy. And as long as you can provide the authorizations for the primary keys and create and the primary key, you can technically use any other hierarchy. So why choose endorsement primary key then? Because it is a key that has been certified by the manufacturer, it provides a trust anchor on this TPM. So using this trusted key or trusted anchor to trust another key that is not been certified. And that signing key can come from any other hierarchy as well. It does not have to come from the endorsement hierarchy. It can also come from a ephemeral hierarchy starting from the null primary seed. And you can use this as well. So why do we use the endorsement hierarchy keys, both the primary and the secondary? The primary key is straightforward because we have a certified key from the manufacturer, and that's why we use the endorsement primary key. What about the endorsement hierarchy secondary keys or the anonymous keys? To tell them apart, let's take a deeper look at the attestation code. So inside the attestation code, we have, from a root of trust of storage perspective, a partitioning of data that is going to identify the specific TPM, and also there is data that is more generic and cannot identify specific TPM. So inside the code, there is data that cannot identify a specific TPM, and that is the PCR itself, the type of attestation, because there are other type of attestation. So here we are dealing with the code type of attestation. And then we have a non-studio that is sent by the relying party to make sure that we are sending fresh attestation codes. And then we have some magic data, which is essentially a TPM generated fixed value that is going to vouch that all the information that is going to be signed is within the trusted boundary of the TPM. And then some signer information about the key. Personally identifiable information includes the firmware version, the restart count, the reset count, and some clock safe data that might be very specific to a specific TPM that has gone through reset and restart cycles. And that can give away the identity of the TPM. So if you use an endorsement child key from an endorsement hierarchy or signing key from an endorsement hierarchy, you get access to all of this, which is including the identifiable and non-identifiable information. And you can basically sign the code using this key. But if you're using any other key, the TPM is going to perform something called as obfuscation, which is basically randomizing all the personally identifiable information and block that information. There are a couple other type of attestations like audit digest and session audit digest that are completely blocked and not randomized. And that's just a side note. So it's an additional piece of information called as NV clock that TCG classifies as non-personally identifiable information. But for the paranoid, NV clock, though it is not fixed in value, it moves at a fixed rate. So you could make predictable predictions about the future anonymous key based on this information. And I mean, the only way to get around that is you could reboot the platform every time you attest. And that's again just for the paranoid. Peter went over this about the PCR being reflective of the software state of the system. But quickly, this system actually enables the root of trust for measurement to ensure that the PCRs are allocated under the RTM control. And there you can set up the authorization policy and value. And then you can also actually have authorizations for the extend and reset operations for the PCRs. And then why trust the keys, where the keys are stored. So this is basically talking about where the keys are protected on the TPM. The sensitive portion of the key that is generated on the TPM never actually leaves the TPM. And it lives in one of three locations: within the RAM as transient objects, or it is moved to the persistent storage as a persistent key. And then if since TPM is a low memory device, you can offload it to the attested system software, and that is wrapped and encrypted using a TPM root key. There are some dictionary lockout mitigations, which basically tells you or blocks the brute force attacks on authorizations. Essentially to say, if you try 10 authorizations, you are and fail it, you are basically locked for like an hour. So we want to now draw some summary from our talk, and we'll talk about the privacy responsibilities of all the roles. In general, logging is a problem and goes against the privacy goals. We should avoid any direct paths between the verifier and relying party regarding specific credential activations. So as an example, if you have a verifier log and a relying party log, let's see the information that they have. The verifier log has the information about the anonymous key names and the unique keys. And if he logs the time at which these were activated, and then combine this with the relying party, which also has access to the anonymous key names and the time log. And in addition, it also has access to the anonymous key public. And if you remember, like if you combine the unique keys and the anonymous key, you are basically compromising the attester identity. So despite the fact that the attester didn't give out the privacy sensitive information, you could actually combine logs from a verifier and a relying party and compromise that attester identity. So prevent a direct path between them. And then additionally, once you compromise that, you tag the time and the anonymous key names, and you can track what specific activities the attester platform was up to. So the message is clear: do not log. It's just like all the VPNs do not log. So these are all the attester platform responsibilities, and we just want to highlight a couple of them here. Basically, this is a misconception that the same entity that does credential activation is also going to verify your attestation codes. But remember, like if you do this, you're going to basically give the unique and anonymous identity to the same entity other than the attester TPM, and that entity can potentially compromise your privacy. So avoid giving the attestation codes to the verifier and give it only to the relying party. Another thing that is important is all attestation frameworks today, as far as I can tell, is they go for the endorsement hierarchy keys for attestation codes. So if your attestation framework is designed around just relying on PCR values, you should avoid using signing keys from the endorsement hierarchy and instead use the attestation signing keys from any other hierarchy. And we saw that credential activation works likewise, and you can create trust anchors between any other hierarchy anonymous keys and the trusted anchor endorsement key. These are some additional system responsibilities for the root of trust of measurement. But the most important one here is that you don't extend platform unique measurements so that your attestation codes look unique to a specific platform. That also gives away the privacy. These are a couple of demonstration slides where we are talking about credential activation of non-endorsement hierarchy keys. You can see that you create a trust anchor with a endorsement hierarchy. Excuse me. And then you have a attestation signing key coming from a non-endorsement hierarchy. And you basically running through the credential activation process, and it is able to succeed in that credential activation process. And you can see that the comparative data here is equivalent. And here we are basically demonstrating the codes that are signed with keys from the endorsement hierarchy. You can see that the personally identifiable information, reset count, restart count, and firmware version and safe flags, these are all in clear and they are not obfuscated. Additionally, the non-personally identifiable information, the PCR digest, it's also non-obfuscated. And flip that around and use a attestation signing key from a non-endorsement hierarchy, and you can see that that value which is personally identifiable information, is completely obfuscated or randomized. And then the non-personally identifiable information, or the PCR digest, is not obfuscated. That is all we had in this presentation, and we will hang around for your questions. And Peter?
Yeah, thank you. There should be the summary slide. Yeah, thanks for your attention. I hope you liked it, especially Imran's explanations about how to preserve your privacy using the TPM-based attestation. If you have any questions, we are still in the venue-less system. Talk to us, chat to us. Also, head to the TPM2 software GitHub.io page. We have a GitHub, we have a Slack, we have an IRC mailing list, whatever. Really approachable community. So if you have any questions, there's also all the tutorials Imran showed to you as an interactive tutorial on the webpage. So if anything was too fast, you can just read it up there again.
Oh, I don't think that was too fast. Thank you very much for your talk. You've landed right on the mark there. That was a great talk. So to our audience,